I will say a few words before we begin. Hello, everybody. Thank you for joining. My name is Victor. I'm an engineer in development. I've been working on memory security already before I was in development. So a few things I wanted to mention. So you may know Welcome from the Product Security Summit that we host annually in San Diego. And there I met Antrix, or well, I met him before, but I talked with Antrix in the last summit in San Diego, and we talked about adding a track to hardware I/O on DRAM and memory management for this next edition in notice. And Antrix asked me if I could help to invite speakers and set up a track, and then the most speakers entering the room. I said yes because, of course, I think memory security is important. It's an important research area. Doesn't get all the attention it deserves. Also, it's a lot of fun. So I think it's great that Antrix is setting up this track. Our goal was to get memory security experts together in the room with speakers from both industry and academia. So we then invited some people that we thought would be maybe have good content for this track, asking them to submit their new proposal with some new content, which here. And that was last May. Now it's October, and here we are. I think we managed to set up a very interesting track with diverse speakers and diverse topics. I'm very excited for today and for the talks that we will see. So I would like to thank the speakers in front for contributing and coming here. Also, I would like to thank the audience for showing up. Welcome everybody to MemSec. And now it's my pleasure to introduce our first speaker, our keynote speaker. And he has a very extensive biography. I will not read it out loud, but a few highlights that I wanted to say. He is a keynote speaker, has an interest in computer architecture, computer systems, hardware security, and bioinformatics. His work has influenced industry and has been employed in commercial microprocessors and memory storage systems. Our speaker started the computer architecture group at Microsoft Research and held positions at Intel, AMD, VMware, and Google. Now our speaker is currently a professor of computer science at UTS Zurich. His work has received many honors from industry companies like Google and Intel, but also from the academic community. And finally, our speaker is what I think an influencer, because his YouTube videos have over 5 million views. You can watch them online for free. Videos on computer architecture and digital logic design. We're going to talk about Onur, Professor Onur Mutlu. Welcome. Thank you for joining. I'm really looking forward to your talk on the future of computer architecture and hardware security. This will be an interactive talk. So if you have questions, just raise your hand or start asking your questions right away, and then we can speak the questions. Help me please in welcoming Onur.
Thank you. Hey, thank you very much, Victor. Should I use this one for recording purposes or?
Yes.
Yes. Okay. That's a good question. No. How about?
Yes.
Whoa. Is there a way to reduce it or?
Maybe you can lower it.
Lower it like this. How about keeping it here? Is it still good? What do you think? No. Okay. If you don't recommend it, I'll try to stay away from it then. Okay. Okay, I'll just keep it here. If it becomes too uncomfortable for people, please let me know. Thanks, Victor, for the introduction. It's a great pleasure to be here. It's great to see a memory security track in this conference, certainly. I hope it continues into the future. I have this grandiose title, which may disappoint some of you. This title is due to Victor, because he invited me for another summit in the past, and he suggested a grandiose title. And I'm going to talk about some things that I see are interesting in computer architecture and hardware security. But first of all, this is going to be a high bandwidth talk. If you don't want me to hammer you, please ask questions, raise your hand. I'm going to give you an overview of what I think computer architecture, where I think computer architecture is going today, And I will focus on especially three major hardware issues: technology scaling problems, system complexity. I won't talk a whole lot about that. And then I will talk about new architectures and technologies. I believe all of these affect security, some of them more easily so, especially the technology scaling problems and system complexity. But new architectures pose some new security issues also, like processing in memory, etc. Okay, so I will start with why do we do computing? When I teach computer architecture, I start always with this. And since we don't have a lot of time, I will give answers also, but you may have answers to this. We want to solve problems. Why do we solve problems? So that we can gain insight. And Richard Hamming, in his beautiful paper, that he suggested that we don't want crunching numbers. Our goal is to really get insight in the end. Why do we do that? To enable a better life and future in general. So how does a computer solve problems? By orchestrating electrons in modern technologies. This may change into the future, who knows? But today's dominant technologies all orchestrate electrons. To orchestrate electrons, we need to speak the electron language. Unfortunately, I don't know anyone who speaks the electron language as humans. So we build abstractions to communicate with electrons and make electrons do what we want them to do, right? So we transform the problem into algorithms and then implement them in programming languages and then execute them on system software and hardware in combination, and then implement the hardware in microarchitecture, logic gates, and then physical devices which operate on electron principles of physics. This is the narrow view of computer architecture. Usually when people think about traditional computer architecture, it's the interface and the microarchitecture. I'm going to take a much more expanded view today, and I'm going to justify it because we're having a lot of issues in actually doing things only at this level. We really need to rethink everything that we're doing from the algorithms to the devices. And this is already happening in industry. That's not new, in my opinion. So this is the expanded view. So what is computer architecture? It's really the science and art of designing computing platforms, the hardware, interface, system software, and the programming model. This is the expanded view, to achieve a set of design goals. Your design goal is really dependent on what you're trying to build. It could be a supercomputer, highest performance on Earth on workloads, AI, LLMs, for example. Or it could be a mobile computer, longest battery life in a given form factor that is cheap enough. Or it could be a general purpose computer that tries to achieve the best average performance across many workloads, right? In the end, designing a supercomputer is clearly different from designing a smartphone, but many fundamental principles are similar. And they're getting even more similar today because we want to expand, we want to get the maximum efficiency and performance out of all of these platforms. Just to give you an idea of what we're talking about, I'm just going to flash some pictures over here. These are computer architectures for different purposes. This is Mr. Bean's computer architecture for self-driving car. I like this one a lot. He doesn't trust this self-driving car. He controls it himself. And other self-driving cars, maybe bioinformatics processors. These exist in everyone's pocket, I believe, some form of it, at least. This is a data center. This is a supercomputer, yet another supercomputer. This is a machine learning supercomputer, if you will, that uses systolic arrays to accelerate machine learning computations. A newer version of it. I cannot keep up with all of these pictures, as you can see. Self-driving car computers that actually have safety potentially built into them. We'll talk about that. And these are actually not just chips, but they're actually systems. I like these slides from Tesla that talk about how they actually not build just the chip, but actually do the entire cluster and the software to enable that chip to be used in the entire system. And this is what the approach that I'm talking about. This is really happening all over industry. This is a GPU. There are newer versions of it. And this is a wafer scale chip. These folks at Cerebras are building chips that are this large so that they can put a lot of compute and memory together for machine learning workloads, at least that's the goal. I hear some ringing over here. Is it? Okay, how do I do that? Yeah, that'd be great if so that I can still hear what people are asking later on. Yeah, but these are huge chips. So people are really trying to do these new architectures, build these new architectures to tackle the efficiency and performance problems that we're having. But always consider that this is a chip, but in the end, you need a compiler and the software stack and the operating system to run workloads on it. So it's really an entire stack that people are designing. Cerebras is not just a hardware company, it's also a software company to enable this. Okay, I could keep going, but I will refer you to many like websites that talk about these chips. But I think it's clear that today, if you want to get the highest efficiency, performance, and also I would add robustness to it, we must really take an expanded view of computer architecture, co-design across the hierarchy, algorithms to devices, and specialize as much as possible within the design goals that we're targeting. Now, I think the question also I'd like to ask is, what limits us in computing today? And I would argue that it's definitely not applications. People are good dreamers. They will dream, and applications will always come about. In the old days, when people designed the MIPS R2000 processor, people said, we don't need a better processor than this. This is the best we can do, and we don't need higher performance. And that has been proven wrong and wrong and wrong and wrong. We will always have better applications coming, and we will always have need better computers. Because as applications push the boundaries, computing platforms will become increasingly strained. And at the same time, we have many metrics to optimize for. This is a small collection of it, clearly performance, energy, correctness, robustness, which consumes, which includes security, cost, programming ease, usability, scalability, simplicity. And this becomes challenging, especially when systems and hardware becomes more complex. So with that backdrop, I would like to now focus on three major limiters that I think are important, especially from the security perspective, but also generally performance and efficiency perspectives. We'll start with technology scaling and talk about system complexity, and then finish up with processor-centric designs that are not keeping up today. And all of these affect all metrics we care about in the end. And I believe they have fundamental impact on security and how we build secure systems. And we really need to understand the implications on all of these on security better. I don't believe we have a good enough understanding in everything. In my opinion, we have better understanding in technology scaling right now, but even there, I believe we need to discover new things. So let's talk about technology scaling. So what is technology scaling? Essentially, circuit size and energy reduction has enabled continuous innovation at all levels of the computing stack. Essentially, you scale the size of a circuit, it improves performance, reduces the size, as well as improves energy. And as circuit becomes smaller, they become less reliable. And more flaky circuits are a problem for robust, reliable, secure, and safe operation. And if circuits start producing wrong results, and they're already producing wrong results today, security can be affected, along with many other metrics like safety, reliability, availability. So that's the key. Now let's take a look at implications of this. I use this picture in my freshman class to motivate this sort of issues. We build infrastructure today. Computing is the biggest infrastructure that we've ever built as humans, in my opinion. But there are other infrastructures people have been building for thousands of years, like bridges. You would argue that this is an important infrastructure, clearly, maybe not as important as computing. But if a bit flip happens in this bridge, this is what happens. And it's a safety problem, security problem, reliability problem. Do people know where this bridge is, by the way? Yes? Tacoma Narrows Bridge, exactly, yeah. Are you a civil engineer? Okay. Architecture and civil engineering, people study these things. New bridge works, but there are two bridges. They actually have, yeah, I've crossed that bridge many times. Not this one. I'm not old enough to cross this one. This happened in 1940. Yeah, great. So this is another example. These folks are constructing a major city, and they're very happy right now. But if a bit flip happens in this road, they will not be happy. So in my opinion, I think we need to think much more broadly about security going into the future. You may argue that, you may criticize us as being too broad, but I believe security should really be about preventing unforeseen consequences. Because when we actually build systems, they will operate under unforeseen consequences into the future. Even general purpose systems are operating under unforeseen consequences. Think about going into space. What will they see out there? Okay, I think Mr. Bean will not be very happy if a bit flip happens in this car, right? And it's good to question how robust these platforms that we may be building into the future. So I think a huge challenge and opportunity for future is robustness, reliability, security, and safety. I'm going to focus on a specific issue in robustness, which is the RowHammer problem, which we have worked on for a long time. Essentially, this is the fact that you can predictably induce bit flips in commodity DRAM chips. Essentially, all recent DRAM chips are vulnerable to this. And I believe this is the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. That's why these good folks are writing articles that look like this. I like this one because it says, forget software. Now hackers are exploiting physics. Don't forget software, but you get the point, right? So basically, we've done a lot of work in this area. I'm going to give you some examples, but not the full treatment because we don't have time. But one can predictably induce errors in DRAM memory chips. This should not be happening. You should not be able to induce any error in a DRAM chip, let alone predictably. There are soft errors we can maybe tolerate, but that's a different thing. Okay, this is known as the RowHammer problem. So why does this happen? Essentially, it's a very simple mechanism. If you look at any memory array, it looks like this. It has a two-dimensional array, rows and columns of cells. And if you want to access a bit in one row, you need to activate that row, meaning you need to apply high voltage to that word line. Now, if you want to access some other bit in some other row, you deactivate or pre-charge the array, apply low voltage. And if you keep doing this repeatedly, which is a legal action, activate, pre-charge, activate, pre-charge, activate, pre-charge, activate, pre-charge, enough times before the cells get refreshed, it turns out in vulnerable chips, some physically adjacent cells flip. They lose their charge. And they go from 1 to 0 or 0 to 1, depending on the encoding. Clearly, this should not be happening. We're not modifying anything in memory, let alone modifying something else that is not belonging to the row that we're accessing. And these rows may be belonging to the operating system, page tables, some other application, your own application. It doesn't matter. This should not be happening. We call this the hammered row. We call these the victim rows. And we basically showed in our original paper in 2014 that this is a technology scaling problem. In newer chips, we were able to induce these bit flips because we were able to induce enough hammerings before the cells get refreshed in the DRAM. In older chips, we were not able to induce these bit flips. So as cells became smaller and smaller, they became more vulnerable to this sort of noise. And this has enormous implications in the upper layers of the transformation hierarchy, because if you get a bit flip at these green levels, then everything that you do over here may be affected because it gets exposed directly to your data structures and algorithms, because we're talking about physical memory, main memory. Very quickly, why is this happening? This is happening because the cells are too close to each other. If a cell is too close to another cell, you have electrical interference between the cells. And whenever you do activations, that electrical interference is reducing the charge in vulnerable cells that are physically adjacent. And if you do this hammering enough times, you reduce the charge enough times from the cell that the charge gets depleted and you lose the value that's in the cell. It doesn't happen in every single cell. It happens in vulnerable cells, but you can figure out which cells are vulnerable and which cells are not vulnerable. So when we wrote the paper, we also actually released this code, which is actually a very simple x86 code, which avoids the caches. It avoids the row buffer in DRAM. And it basically ping-pongs activates the rows X and Y and induces bit flips if the chip is vulnerable. We also said that if you actually sandwich one row between X and Y, you get a lot more bit flips. Okay, and we show that this happens in real systems and you get bit flips. And later work actually replicated all of these results, so I don't want to spend a lot of time on these old results. So what's important for security? When we wrote the paper, the first sentence we said was, memory isolation is a key property of a reliable and secure computing system. And access to one memory address should not have unintended side effects on other addresses. And I still strongly believe this. We should really maintain this invariant so that we can build better systems, the isolation invariant. And we said in the paper that someone can use the program that we wrote to hijack your computer. We didn't show that exactly, but these good folks from Google Project Zero read our paper, replicated our results, and they basically developed an attack, or multiple attacks actually, where they could, in one of the attacks, they could take over a system using a user-level program. I'm not going to go through all of these security implications. There's a lot of literature. I'm going to flash some papers that we have written, and other people like Herbert has done a lot of work over here. Victor has done a lot of work on RowHammer. But essentially, one can exploit RowHammer to take over a system. If they cannot take over a system, they could read data that they do not have access to, so you can break confidentiality. You can break out of virtual machine sandboxes. You can corrupt important data, which may render, for example, machine learning inference useless. Otherwise, a 99% accurate machine learning accelerator could become 10% accurate, potentially. People have shown this multiple times. Or you could steal secret data like crypto keys or ML model parameters. So you could do a lot of interesting attacks, and security literature is full of this, which is very exciting and interesting in my opinion. I will summarize RowHammer with this quote from a famous hacker on Twitter. This famous hacker says, RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you're after. I like this analogy. So if you're stuck in this room, don't worry. Keep banging on the wall and magically the door will open if RowHammer is in effect. Interference. Okay, so let me give you some more about RowHammer. We built a lot of infrastructure, this FPGA-based infrastructure, to test DRAM chips to understand these issues. And I'm going to give you some results on this topic. You can find this infrastructure online. It's all open source. We'd be happy to help if people are really interested in understanding what happens, what is lurking in DRAM chips. This is the most recent one where we can test DDR4. This is the original paper. And we wrote a lot of papers on this topic that talk about the issue. So if you want to learn more about it, these are the papers. And Girai's recent thesis is probably the most recent thesis that goes into a lot of experimental insights in modern chips. So the solution, and we actually built a lot of understanding of the problem. I don't believe we have a complete understanding yet. For example, how does aging affect RowHammer? I don't think that is solved at this point. We're looking into it, but there are a lot of complex interactions. How does temperature affect things? There are a lot of interesting things to examine that we don't know fully. But let's talk about solutions. I think the solution that we've always argued was to build much more intelligent controllers. We said that it's very difficult to solve this technology scaling problem without moving to some other technology, which we will very briefly talk about. They all have issues in the end. So we should take a system level approach and design intelligent controllers to overcome these issues. So if people have been working on storage, SSDs, for example, they could understand the solution, I think. If you look at flash memory, NAND flash is a technology that doesn't work. What do I mean by that? Basically, the cells are actually, by nature, completely error-prone. What makes these cells work is the controller. The controller really adjusts the voltages, make sure that the cells are programmed in the right way so that you can actually get real good results out of that chip. So we would like to see that in DRAM as well. We've been arguing that for a while. And finally, the industry is, I think, moving in a direction that I believe is similar to this. I'm not going to watch for the perfect correctness of this and all of this, but this is SK Hynix. They wrote a paper in ISSCC, the Major Circuits Conference in 2023, where they introduced essentially intelligent controllers. Very quickly, this is a mechanism that was later adopted by JEDEC, which is per row activation counters. Inside the DRAM chip, you have counters for each row, and the DRAM chip somehow counts how many activations each row receives. And if the number is greater than some threshold, it takes some mitigating action. Not all of these are exposed. This is mostly security by obscurity in general still. Unfortunately, I think we need some movement toward better security, better exposure of security mechanisms. There are papers on this topic from Samsung. There's a paper from Microsoft, which looks very similar to the SK Hynix solution. And this was recently adopted in JEDEC. Now, we have evaluated this, and we have found that there are actually some issues with this solution. This may be vulnerable to denial of service, and there are performance problems. I'm not going to talk about this in detail. But I think I will raise the question, are solutions good? This is a solution. And I can bypass the solution, right? So basically, are we bit flip free in 2024 and beyond? I don't believe so. This is a paper that we published in ISCA 2023, and we always ask the question, what if there's another phenomenon that doesn't require a high activation count? A lot of these solutions work by detecting a high activation count. And if you can actually induce a bit flip before that high activation count happens, you can bypass all of those solutions. And we've shown, for example, in this paper that row press is another disturbance mechanism that's in effect. In RowHammer, you keep activating a row as frequently as possible. In row press, you keep activating a row, but you keep it open for some time. And if you keep it open for some time, it turns out you get a lot more bit flips a lot earlier. Just to give you an idea, you can amplify read disturbance and reduce the number of activations to induce a bit flip by 1 to 2 orders of magnitude. So if you have configured your solution based on the characteristics of RowHammer, which is over here, it doesn't work. Row press based, you can circumvent it with row press. And we've actually shown the proof of concept where we could induce row press bit flips in real systems. And we've actually combined RowHammer and row press. Other people have independently verified. I think Jonas is going to give a talk later today, independently verified and developed attacks using RowHammer and row press together. And interestingly, this phenomenon was not known at the device level. This was surprising to us. Well, known. There were some patents on this topic that are extremely vague. But people in the device community started investigating what's happening underneath based on the results. And they actually started understanding what's happening underneath. I find this very interesting because you could actually do research at the architecture level on a phenomenon that was not exposed at the lower levels. And the lower level folks get excited and they actually understand what's going on. I believe there's a lot more to discover. So the takeaway, I think read disturbance is a technology scaling problem. Finding a good solution to read disturbance is difficult. And I believe this will become more so. We will find more and more effects. So there's more to come. There's lectures, etc. So you can say, I don't care about DRAM. Hopefully, this audience doesn't say that because DRAM is really the main memory market today. But if you're looking into the future, 10 years down the road, you say, there's some emerging memory technology that's going to replace DRAM. I would argue that all of them are going to be vulnerable to this sort of effects, and we need to plan for that. And I believe that DRAM's future is going to be DRAM for some time. Maybe 3D DRAM can actually reduce some of these effects, but we can talk about that separately. Okay, so I think the takeaway is we need intelligent controls to enhance security and enable better scaling. If there are questions, I can quickly take them, but we can also defer them to the end. Okay, that was memory. Data corruption actually is in CPU logic too. So there are intermittent defects that cause silent data corruption. These may be happening because the CPU is designed for some temperature, voltage, and frequency levels. And for under some conditions, like under some data patterns, under some voltage fluctuations, you may actually get an error, wrong bit latched to a register. And people have talked about that. I'm going to briefly mention that. And these may be very hard to detect or replicate. They may be potentially exploitable. I have not seen an exploitation of this yet. And the Facebook and Google have written papers on this topic. This is not a new problem, but it's a new problem in the sense that people have been observing this in the large scale because if a CPU fails in a data center, it may be failing every day because you have hundreds of thousands of computers, right? So this is from Google's talk. They call it mercurial cores that lead to corrupt execution errors. If you're interested, you can take a look at it. And there are papers on this topic, especially in deep learning accelerator systems. And also, this is a paper from Alibaba that talks about silent data corruption in their data centers. I'd recommend people to take a look at it. I'd be happy to talk about it. As I said, this is not a new problem. People have been working on avoiding this sort of errors. In fact, our group has done work in this area that I'm not going to talk about. We've always argued, again, a system level perspective. Software should be equipped to detect this sort of errors. And these are papers from all times. I'd be happy to talk about them if people are interested. So if you can design chips that can test themselves online with intelligent controllers once in a while, you can actually overcome some of these issues. Okay, so I think this is the end of my first part of the talk. Both memory and logic errors will become worse as circuit size reduces. Hardware errors will create worse robustness problems. And I think we cannot afford to ignore data corruption. Some people may think, may want to believe you, may want to make you believe otherwise. They actually exist. I've seen them. I've talked to them many times. But if you really want to build robust systems, you cannot afford to ignore data corruption. I'll jump to system complexity. I'll do a very quick overview of this because I think this is a problem that we are ignoring in general. This also ties in nicely with the emerging technologies that I'm going to talk about. Essentially, today we're building very complex systems. They have many hardware components, and these are complex components. I'm not even talking about software at this point. As complexity increases, the components become harder to design and verify. Operational behavior becomes harder to reason about, and there are many things. Correctness becomes harder to reason about. Performance, energy, security, privacy, all of those become harder to reason about. And also it becomes harder to control interactions between components and avoid information leakage. And at the same time, old methods do not keep up with new trends and complexity. I'll pick on virtual memory very quickly in the rest of this part. But there are also other methods like coherence. We've been designing coherent systems. We've been doing verification. These methods really are not keeping up with the complexity of the systems that we're building. So this is complexity. This unfortunately stopped at 2020. I haven't updated, but clearly there are a lot of transistors that we're adding to our systems. We're already at trillion transistors in the wafer scale chips. And these are general purpose CPUs. You can see there's a lot of complexity. Memory hierarchies are complex. And on top of this, we're adding complexity at the third dimension, also 3D systems. So I believe side channels will not go away. This complexity leads to endless side and convert channels. Clearly, Spectre, Meltdown, and their variants are examples. These will not go away. They will become worse. On top of this, this complexity leads to many bugs and unintended behavior, especially when you add new features to a system. For example, when virtualization was added to general purpose CPUs, the bugs increased significantly. And some of these could be exploitable. That's good to understand. So the question I ask is, how do we tame processor complexity and resulting issues? I don't have a good answer. I'm just going to put the question out. But I'm going to pick on one thing that we've been doing for 60 plus years that has not changed much, which is virtual memory. Essentially, access control and protection mechanisms that we have in today's systems at software level, software hardware cooperative level, are based on virtual memory. And virtual memory has not changed even after decades of technology scaling and memory system improvements. Today, we have huge memories. Sometimes virtual memory is not needed in many applications. Yet we still use virtual memory in general. So it causes large performance problems and is responsible for large complexity, power, and energy in processor chips. If you look at the memory hierarchy, there's memory hierarchy, and then there's the virtual memory metadata hierarchy to actually translate so that we can access the memory hierarchy. There's a lot of complexity there. It's very poor for fine-grained security and access control, which we have been ignoring for a really long time, in my opinion. And I think virtual memory in general hinders innovation. Whenever you build accelerators, heterogeneous memory systems, heterogeneous architectures, processing near data that we will talk about, you need to deal with virtual memory. And virtual memory complicates everything in general. I believe it's time to rethink virtual memory. This is already happening, I think, but there needs to be more effort in this direction. This is actually a slide from my freshman class. I talk about virtual memory in lecture 26 of my freshman class. And I say virtual memory is actually one of the most successful examples of hardware-software cooperation, architectural support for programmers, how to partition work between hardware and software, and program-architect trade-off. Maybe not so going forward or anymore at this point, because there are many trends that virtual memory doesn't consider in general. Again, I will not talk about this in detail. We have some work in this area that I'm happy to talk about, but there are also other works in this area. I think we still need to revisit virtual memory completely. This ties in nicely with what I'm going to talk about next, because one of the major challenges of processing near data, processing in memory, is really how to handle virtual memory. And I don't think that problem is solved yet. Okay, let's talk about new architectures and technologies. I think this is actually very exciting and interesting because this can have a large impact on security and robustness for good and bad. We can design the new architecture completely with security in mind, or we can ignore security and say, let's do it as afterthought again. I hope we do it the first way and not the second way. I think ideally we want security as a first-class design goal, but maybe the train has already left the station over here because there are some new architectures that are being developed that have not considered security as a first-class constraint, but this could change with people like you over here. So I believe there are multiple potentially paradigm-changing new technologies and architectures like processing in memory. I'm going to focus on that. Accelerator-based computing is already happening, but still we have issues over there. And I know nothing about quantum computing, so I'll leave that to the experts over here. I think there are also emerging memory technologies that I left out over here, but that's also, I'm not going to talk about that. Let's talk about processing in memory. So essentially today, we have a huge data bottleneck in our systems. And important workloads are all data intensive. They require rapid and efficient processing of data. We can generate more data than we can process, and we want to do more sophisticated things on the data. Clearly, machine learning is a great example. Genomics is another example. This is a talk by Cerebras' CTO, Sean Lee. These are the guys who are building these wafer scale chips. And it basically shows that memory model requirements are growing, and or memory requirements are growing, and compute requirements are also growing exponentially. You can see the numbers are crazy, right, in the end. So we want to put a lot of compute and a lot of memory together. Their solution to this problem is building wafer scale chips. In a wafer scale chip, you can put a lot of SRAM together with a lot of computation. Unfortunately, SRAM is not the best technology if you want high capacity. So the amount of memory they have is, I think, 80 gigabytes or so, which is nothing compared to the amount of memory that we want to have in genomics and machine learning, et cetera, today. So I'm going to talk about a different solution. So in genomics, data is actually growing much, much faster, which we do a lot of work. In my opinion, we have actually even more responsibility going into the future. We're building the biggest infrastructure in the world. And do we want a world that's sustainable and livable, or do we want a world that doesn't exist anymore? And this is already happening. I'm serious about this. People are actually building huge data centers that's really choking the world's power. And it's going to get worse and worse if we don't have some solution to this. Now, that said, I think human beings are greedy. We want high performance, energy efficiency, and sustainability all at the same time. So how do we get that? Before getting into how do we get that, are we doing the right thing today? And my answer is no. We're designing systems that cause great energy waste because we're moving data between the processor and memory. And the large scale also, we're moving data across different components of the system. This data movement causes great energy waste because data movement is expensive, as we will see in a little bit. This causes a lot of performance loss also. I put this in parentheses because we clearly realize that. We build our systems to be much, much more complex to overcome the performance loss. We build huge amounts of cache hierarchies. We build a lot of prefetchers. We build huge out-of-order execution engines. We build massive amounts of multi-threading, etc. All of these come at a cost. And that cost is a complexity that we talked about previously. We don't recognize that in general. That is sunk cost. So, okay, very quickly. Essentially, we need to rethink how we design our computing systems. Today's computing systems are quite processor-centric. All data is processed in the process at great system cost. Yet we know that memory is a problem. I will go through these relatively quickly. People have said that it's all about the memory, stupid. This is Dick Seitz, who is a chief architect of alpha processors in 1990s. They basically built the fastest alpha processor, and he said that this beautiful processor is capable of finishing 4 alpha instructions per clock cycle. Unfortunately, it's finishing 1 instruction every 4.7 clock cycles on this important workload that we think we designed the processor for. Why? It's waiting for data to come back from memory. This is data from my own PhD thesis. With Intel, we basically showed the same thing. Most of the time, the processor is waiting for memory. Google, in 2015, according to them, all of their data center workloads on the state-of-the-art CPU, it's all waiting for memory, as you can see. Okay, so that was performance. Let's talk about energy. Energy is even worse. This is data from Bill Daly, chief scientist of NVIDIA. This is the energy cost of a memory access, 16 nanojoules. This is the cost of a sophisticated arithmetic operation, double precision, floating point, 20 picojoules. That's 800x difference. Does it really make sense to bring the data from memory to the processor to do a very energy simple operation? And by the way, these numbers are like this because of the success of technology scaling, logic scaling. Memory did not scale very well. Interconnects did not scale very well. Now, if you look at simpler operations, the numbers become even crazier. compared to a 32-bit integer operation, a memory access 6400x energy costly. Now, we're not even talking about storage. If you talk about storage, access to storage, add 10x more over here. And then people are trying to reduce the complexity of arithmetic today, 4-bit arithmetic, multiply that by about, let's say, 8x or so. So the numbers really go crazy. Are we really doing the right thing by moving the data from the storage main memory to the caches and the register file so that we can access data? I believe no. So as a result, we spend a lot of our energy on data movement. These are with Google, works with Google, where we showed that in mobile systems, you spend more than 60% of the total system energy on data movement. And also in large machine learning models in edge neural network accelerators, more than 90% of the total system energy is spent on memory. And if you're interested, for LSTMs and transducers, for example, most of the energy is really spent on interconnect and DRAM, off-chip interconnect and DRAM. Okay, so basically the fundamental problem is processing of data is performed far away from the data. We want to enable computation with minimal data movement. We now want a paradigm shift where computing, where we make the computing architectures much more data-centric. And this is a general paradigm, I think, not just in memory, but also storage, also sensors, also tape, also interconnects, also network controllers. We want to enable processing everywhere, but I will focus on memory. So essentially, we have a lot of components. Why are we actually restricting the processing to a very small fraction of this SRAM-dominated chip? Okay, so we're going to treat memory as an accelerator, and we're going to accelerate some functions. Even with this limited accelerator-based paradigm, there are many questions over here. How do you design the compute-capable memory and controllers? How do you design the processor and communications? How do you design the software and hardware interfaces? How do you design system software, compilers, and languages? And also, how do we rethink our algorithms and also theoretical foundations of computing? So if you think about computing theory, we count operations in the big O notation today, right? But maybe there should be a more data-centric theory to optimize our algorithms. I'm going to go through two quick examples. There are two types of processing in memory. One is processing near memory. The other is processing using memory. Processing near memory is what we're used to today. You have memory, you have processor. Bring the processor closer and closer and closer inside the DRAM chips. This is what Fabrice and his company has been doing in Opnam, for example. And this is actually easier to do, easier to adopt. The other option is processing using memory. You have memory and processor. Forget about the logic. This is memory. This memory is fundamentally capable of actually performing operations, if you look at its analog operational properties. And it can exploit those properties to do computation. There's a lot of work in this area, a lot of like real prototypes that happen in the system. I believe Fabrice is the only one that's commercially available today. But there are also prototypes from Samsung, SK Hynix, Alibaba, where they all built their DRAM chips. They put processing logic near each bank in all of these, either general purpose processors or accelerators, etc. And 3D stacking technologies enable actually a lot of possibilities that people are going to exploit into the future. And with CXL type of interconnects, I think there's a lot more potential because we can do offloading more easily. Let me give you some quick results. So if you have 3D stacking technology, you can put logic underneath memory layers, and this logic can have high bandwidth, low latency access to the memory layers. And this way you can actually, you don't need to go to some farther away logic to do computation. We've done a lot of work. I will not go into a lot of detail since we don't have a lot of time, but you can accelerate graph processing significantly by building a GPU-like accelerator that is based on these 3D cubes, a distributed system, where you do graph partitioning. And when you do the computation, you don't move the data to the computation, but you move the function to the data whenever you do that. Okay. And you get significant performance improvements like 13x and energy reductions. Using DRAM, you can also do other things, like we can support bulk bitwise operations, copying, and or not and majority operations, true random number generation, physical unclonable functions, and more complex computation as well. You get significant performance benefits, energy benefits, even in commodity off-the-shelf DRAM chips. So let me give you one example of copying. So today, when we do copying, you go through the processor. Why not actually do it in memory? If you show this picture and you say to your 10-year-old child, for example, I do copying by going through the processor, they will probably tell you, why don't you just do this? So this is very interesting, I think. Since we don't have time, I'm not going to go through the details, but you can improve page copy performance by at least 10x and energy efficiency by more than 70x. And there are a lot of results on this paper, on this topic. Existing DRAM chips are actually quite capable. We have built infrastructures like FPGA-based infrastructures, which is also open source if people are interested in this. In this infrastructure, you can have copy operations and random number generation operations shipped to the memory controller of this FPGA, of this RISC-V system, and the memory controller violates the timing parameters in the DRAM to do the copy. This works mostly reliably, as I will show you in a little bit. And you get significant improvements in terms of copy and initialization performance. Okay, so what is mostly reliability? We have recently demonstrated that you can actually do in real DRAM chips that are not designed for this purpose. You can do copying with more than 99.98% success rate. Remember that DRAM chips are not designed to do this. We're actually abusing the DRAM chips to do this. You can perform bitwise NOT. You can perform all types of bitwise operations, and I'd be happy to talk about that. On top of this, you can implement physical unclonable functions in DRAM, real DRAM chips, by violating the timing parameters, random number generation, etc. And in the flash chips, you can also do similar things, but I'm not going to talk about it. So, okay, this is very interesting. I think there's a lot to do over here. This changes the paradigm. There are a lot of adoption issues that I'm not going to cover over here, but security is one of the adoption issues that I'm going to mention over here. In the end, we need to revisit the entire stack to enable this. So what is security? How does security play here? Does PIM make security better or easier? Does PIM make security worse? I think there are many interesting questions here that I'm not going to tackle at this point, but I believe both are possible. PIM can worsen security because RowHammer becomes worse, for example, side channels become worse. There could be new threat models that people have not considered. But we can also enhance security by reducing the exposure of data and keys outside. We can more easily implement things like homomorphic encryption and cryptographic hashing inside memory. We can support security primitives better on the memory side. In the end, if we actually push the security infrastructure completely in memory, maybe we're actually less vulnerable. In my opinion, this is the case, but this needs to be proven going into the future. So I'm not going to go through this, but we have some papers on this topic that I'd be happy to talk about, and we give talks also. So let me conclude. I think I've covered a lot of things, but technology scaling is not going well. System complexity is increasing. We have a lot of old methods that are not keeping up, and processor-centric designs are not keeping up. And I think we need to consider a lot of things that we do, given all of these trends. I believe these affect not just security. They affect energy efficiency and performance as well. But I believe we should really take security as a first-class constraint. Okay, I'll acknowledge a lot of people who have funded our research. And most importantly, I'll acknowledge the group that I'm leading, the Sapphire Research Group, who've done a lot of this research that I've discussed. All of the papers and code is available online. And this is our GitHub. And if people have questions or if they want to work in this area, we'd be happy to help you get started with a lot of tools, etc. Thank you. I'm happy to take any questions.
Thank you, Onur. Very nice part. Are there any questions from the room?
No questions?
Slide you showed on the processing in memory and moving data within memory without going to the system. What do you know? What is the industry take of this, and what is the status? Is this something that's actively being worked on there? Will we actually see this, or are people hesitant?
Yeah, that's a great question. I mean, in general, whenever you want to push functions to the memory side, industry has been quite, let's say, reluctant because of the way things have evolved. And you need to change the interfaces, which are standard, etc. I think there is much more open-mindedness today on doing things like this. I think this copying operation, for example, is very simple. It requires very little changes. It needs to be reconsidered given the current mindset. Like we did this work 10 plus years ago. And when we talked with industry at the time, for example, people at Samsung was quite excited. We could do this. Who will buy the chips? The question is, what is the market size, etc. If you don't actually put the hardware out, it's very hard to evaluate the exact market size, in my opinion. So there needs to be some boldness in the memory industry to actually enable this sort of thing. I believe that mindset is getting better and better. I'm not sure if we're still there yet, so I'm not sure if I can answer that question completely. But if the hardware is out, I believe people will develop a lot of things to actually take advantage of.
More questions?
Yes, please.
One more question.
Yeah.
I guess in the stack that you had showed us, seems like the base was electrons, right?
Yeah.
Can you maybe theorize a bit if, and it seems to be the root cause of many of these problems, right? If that base now changes, would all of this be irrelevant?
Yeah. That's a very good question. I mean, in the end, physical world, as far as we know, is based on electrons. So at some point, you cannot escape electrons. But maybe you can raise the abstraction level such that you can do, for example, biological computing where cells are the basic things that you talk with. Or you could do more chemical computing where people have tried. Unfortunately, in a lot of those, currently, we're not at the right place yet, meaning there's very little research going on, even though there's interesting research. There's very little research, and it's not clear how we can exploit those. And fundamentally, I think you cannot avoid this sort of issues that we have discussed because everything is based on electrons. Even if you're doing the computing in a biological basis, you're subject to how the electrons move. And at some level, you cannot avoid that, especially if you want to push the like biological circuits, for example, to their limits, as we're trying to do right now. So I believe this is very fundamental in the end, regardless of whether or not you're trying to use the electron abstraction level or something else.
So the synopsis, I guess, is no matter how you look at it, you cannot escape the analog nature and its flaws.
I think so, yes. You can escape at very high cost levels. Like you can isolate things and put them far away from each other. Then you'll have very small amount of memory or very large amounts of memory at extremely high costs.
One more question?
No, yeah.
Maybe also a comment. I watched a lecture from your friend Mutlu about the fact that there is lack of innovation in operating system, and that's why we have growing number of peripheral processors. This seems adding another peripheral processor in the memory. If there will be transition phase between the architecture, which is right now, and moving into in-memory processing. So how you see handling the innovation on the higher layers, and how this will work, how long it will take to transition, because it seems like a huge task.
Yeah, absolutely. So I think that's a very good point. Basically, I think transition needs to happen across all levels of the stack. No question about that. But it will, in my opinion, it will happen over time. Like we need to revisit the stack with a memory-centric mindset. How long will it take? It really depends on the mechanism that you put over here. So for example, if it's a copying operation, simple copying operation, even that requires support from the stack, but the support is somewhat limited. If it's really executing like some operating system functions on the memory side, then you need a lot more support. So in my opinion, we should start simple, start executing some functions, and over time, evolve the software stack as well. It's not, the change is not going to be immediate, but I definitely agree that we need to revisit the entire stack, no question about that. But I believe we have nowhere to escape also. In a longer version of the talk, I say that this problem is not going to go away. This problem of energy and performance of data movement is going to get worse and worse and worse. Even with 3D stacking technology, we'll have actually issues like thermal, so we cannot escape this problem. And so I believe we will need to revisit the stack. And this is already happening. So if you look at some of the chips like UpMem or SK Hynix's chip, people are looking at software stacks that build on top of that. I have not seen a full operating system though. Okay. Not yet.
That would be interesting.
Absolutely. Yeah.
Also bootstrap of these new computers, because I guess bootstrap BIOS will be completely different also.
Yeah.
Correct. That's yeah. It is a very short question.
Okay.
Then yeah.
I'll keep the answer short.
It seems that security and performance, they almost always orthogonal, and you have to find a compromise between very high performance or very high security. So also from the DV side, design verification side, there isn't a lot of tools out there that help you on the security evaluation early on. So I'll be happy to hear your thoughts on that.
Yeah. So I'll keep it short. I think I definitely agree that there's a tension between security and performance, and I don't think we're going to avoid that. It's very fundamental. I agree that design verification doesn't consider security today. That was one of my big points in the complexity also. Design verification is actually not good enough for many, many things we do today, performance, including performance, but security should be there. That said, I truly believe that if we move to a more memory-centric paradigm, we can get both performance and maybe better security if we actually think about how we provide security here, because a lot of the security issues that we have today, well, not everything, of course, but a lot of the hardware level security issues are because of the data movement that we're having. If we kind of fundamentally minimize that data movement and constrain it to the memory device as much as possible, I believe we can improve both security and performance, maybe with a one-shot movement. After that, I think we'll be back to the trade-off space where we trade off security and performance.
Let's thank the speaker.
Thank you.